Hello, everybody again. So you saw this on the last video, the using matrices to solve linear systems. And that's the bulk of this next test. Like I think I said that before. And we ended with this. We have a system of linear equations. The answer is 2, -3. You can convert this to what's called an augmented matrix with just the coefficients. And then transform it into something like this. And this tells you the answer. This is called reduced row echelon form, which we'll talk a little bit about that later. But the big takeaway here is that at any point, there are three matrices here. So you can always convert them to a system of equations. This is 5x plus 7y equals -11, which is from the original system. But that is equivalent to this system. These two lines together, 1x plus 0y is equals 2. So in other words, x equals 2. And 0x's plus 1y equals -3. So in other words, y is -3. So more about matrices, but just a second. What am I permitted to do? How can I manipulate this system while still preserving the final answer? And again, the answer is 2, -3. There's no mystery. The answer is 2, -3. But what am I allowed to do here? What did I do here? This seems pretty silly, but if I solve this system, I would still get 2, -3. And all that happened was I just rearranged the equations. I can, of course, I'm permitted to do that. What else can I do? Well, to solve this, if we were just stuck in chapter 5, which was the last video, you could solve it by what we call the addition method. And here I chose to get the two x's to become opposites. I could multiply, oh, I'm sorry, referring to this one. I can multiply the top equation by 3 and the bottom equation by -5, and that would result in 15x and -15x. I would have to multiply everything by 3 and all these by -5. But what does that mean? That means I can multiply by any number, can't I? As long as I multiply to both sides of the equation, I can multiply it by any number. But then 0 is my favorite number, well, my second favorite actually, and multiplying by 0 would be a real waste of time because if I multiply everything by 0, then I get an equation that says 0 equals 0, and that doesn't help me understand anything. So I'm going to readjust multiplying it by any number to say, well, I can multiply it by any non-zero number. And then lastly, remember after, if you did choose to multiply this by 3 and this by -5, you would have 15 and -15. But what's the point? The point is that now if you add these two equations, you get a third equation, but it's still in the same system. It's still in the same family. This isn't, even though it's a new equation, it's still relative to these two. If I divide both sides by 41, I discover that y equals -3, the part of the solution to this system. So the takeaway here is I can add any two equations and get a third equation. All this can be related to matrices. So when we manipulate matrices, we can add, we can subtract, we can multiply. We talked about that a couple of times ago. But when we're trying to solve a matrix that is representing a system, we do something called row operations. And all the things that we did in that last slide can be converted to a row operation. Remember when we switched the two equations? Well, every equation is represented by a row. So any two rows can be interchanged. I could put row 1 where row 4 is, and then row 4 would go where row 1 is. I can I can multiply any non-zero number to any row I want, and I can add any two rows that I want. What this third operation is usually used in combo with the second operation. Usually, you multiply a row by a certain number, and then you add that result to another row. Okay, so here's the matrix that we've been thinking about. Don't forget, I can always convert this to a system. This is 5x plus 7y equals -11. 3x minus 4y equals 18. What if I wanted to switch these two rows? If I switch the two rows, I get this, right? 3, negative 4, 18 is now on top. Well, the symbols for that is this. This is row 1, this is row 2, and the double arrow indicates that you're switching. You're just switching row 1 and row 2. I can multiply row 1 by 3 if I wanted to, but then I want to keep the results in row 1. So this becomes 15, this becomes 21, this becomes negative 33, like right here. What is the symbol for that? 3 times row 1. So this indicates you're going to take row 1, you're going to multiply it by 3, and you're going to put the answer in row 1. Notice row 2 stayed the same. Row 2 was 3, negative 418, same thing over here. This only tells you to multiply row 1 by 3 and put the answer into row 1. You can multiply row 1 by okay, I'm sorry. I meant to say, what about division? Can you divide by 3? Could you divide by 5, for instance? Well, yeah, you could, but technically, let's just stick with multiplication. Instead of dividing by 5, I get the same result as if I multiply by 1/5. So you can remember, you can multiply by any non-zero number. So multiplying row 1 by 1/5 gives you this, and it's just replacing the original row 1. And each element in row 1 is added to the corresponding element in row 2. So that is row 1 plus row 2. Now take care here, because row 1 plus row 2, you're going to get an answer. Where do you put that answer? You put it in the last row that was mentioned, row 2. So row 1 is going to stay the same. Here's row 1. It's the same, 5, 7, negative 11. What does row 2 look like? You take row 1 plus row 2. So 5 plus 3 is 8. And then 7 plus negative 4 is 3. And negative 11 plus 18 is 7. And that replaces row 2. That's what we did over here. We added these two equations. So you could think of this as adding 2 rows, and you got another equation, so another row. But this new row will replace one of these 2 rows. And for the symbols, it's always the last row that was mentioned that gets replaced. So there are 3 main row operations. You could switch 2 rows. You can multiply any row by any non-zero number, even negatives. And you can add any 2 rows. And again, usually multiplying and the adding get combined together. And we'll see that. So again, with this example, this is what I'm talking about. You're going to multiply row 1 by negative 3/5. And then you're going to add that to row 2. And the result is going to go in row 2. So at the very end of this problem, the very end of this example, row 1 is going to stay the same, because you're taking negative 3/5 times row 1 and you're adding it to row 2. Well, let's first figure out what is negative 3/5 times row 1. Well, negative 3/5 times 5 is negative 3. Negative 3/5 times 7 is this. Negative 3/5 times negative 11 is that. Now, if I add those 3 numbers to the 3 numbers in row 2, I'm kind of doing this in my head. Negative 3 plus 3, negative 21/5 plus negative 4, 33/5 plus 18. I get these 3 numbers. And those 3 new numbers are the result. And the result goes in the second row that was mentioned. So row 2. So there it is. That's what row 2. Remember, row 1 looked the same. And again, I'm going to say this about 100 times. At any stage, whatever the rows are in your matrix, you can convert it to a system, and vice versa. If you have this system, you can make it into a matrix. But what's the advantage here? The advantage here is that the bottom row, let's see what I have. Now I've got 0 x's, negative 41/5 y equals this, which is this equation. So I could solve for y very easily. I could just divide both sides by negative 41/5 and discover what y is. that's what we would do. But now let's practice row operations. Instead of dividing by negative 41 fifths, it's equal to multiply by the reciprocal. So I'll multiply everything in row 2 by negative 5/41. And multiplying 0 by this keeps this at 0. Multiplying for negative 41 fifths by negative 5/41, everything cancels out and you're left with 1. And multiplying this by negative 5/41 results in negative 3. And what do I discover? Y equals negative 3. Ay. But we remember this original equation, y equals negative 3, the x equals 2. So you're probably wondering why go through all the trouble. This is just an exercise to get us comfortable with row operations and matrices, etc. The calculator is going to do a lot of this grunt work for us. All right. Okay. This guy right here, this German Karl Gauss. Whatever you're passionate about, soccer, you got a favorite soccer player, chess, you got a favorite chess player. If you like math, this is your number one guy. This is, until you pick another hero, this is your hero. Karl Gauss, absolute genius, staggering genius. And he contributed a lot to mathematics. And he's named after this process. It's called the Gaussian elimination method. So you got an augmented matrix. Remember, this matrix can be represented as a system of equations. And all these stars are the coefficients in your system. You want to get, it'll be very obvious why this benefits us. You want to get positive ones going along the diagonal from the top left to the bottom right. And underneath those ones, you want zeros. And again, that will become clear why. But the way to do that, he kind of perfected this method, or it's attributed to him. You want to start in the upper left. You want this to become a 1. And then once that is a 1, then you make these two become 0. And then your first column is fixed. Then you move on to column 2, and you want a 1 right here. And then you make the 0 underneath that. And you continue in that process, moving from left to right. You get the 1 first, and then you get the 0. 1, and then the 0. And then lastly, you just get this to become a 1. And once you get it into this form, it's very, very advantageous for us. And we'll see why almost immediately. Okay, so we're going to use the Gaussian elimination and then something called back substitution to solve. So here is a 3-variable system. And this, we should think of this as 3 planes in a 3-dimensional space. So we have 3 vertices, and 3 axes, an x-axis, a y-axis, and a z-axis, and they all have to be perpendicular to each other. How could that be possible? Well, the x-axis, the x-axis is the one that goes left and right. The y-axis has to be perpendicular to that, so it has to be going up and down. There's the y-axis. You need a third axis, z, that's perpendicular to both of these. How would you draw that? It's the one that's coming out towards you, towards your face right now, and back past the computer. That makes it the 3rd-dimensional space, and every axis is perpendicular to every other axis, but we can't draw a 3-dimensional object on this 2-dimensional space. You're going to have to imagine it. Anyway, this is a plane, just a flat sheet, a flat surface. This is another plane, and this is another plane. And the solution to this system is the ordered triple, XYZ, where all 3 of these planes intersect. All right. First of all, we convert this to an augmented matrix. So 3 x's, 1 y, negative 1 z, and then 0. That's my first row. And now I use the Gaussian method. And remember, the ultimate goal is to get this. 1's down the diagonal with 0's underneath. First of all, let's go to our calculator. And let's see here. Let me pause for just a second. Okay, so on our Inspire, we could go here to create a matrix, and this matrix had 3 rows and it had 4 columns. And I plug in the remember I'm plugging in this matrix right here. So 3 tab 1 -1 0. That matrix, that augmented matrix, represents my system of equations. And with the calculator, we go to Menu, underneath Matrix. There are lots of things we could do with these matrices, and I want to do, first of all, reduced row echelon form, RREF. I want to take the RREF of this matrix, so I press up, it copy and pastes, I press enter, and here is the solution. X is 0, Y is 2, Z is 2. So you're always going to have the answers at your fingertips if you got a calculator. With the 84, I think I put this one in. So letter B, matrix B, is that matrix. And for the 84, we go back to the matrix menu and I go to math and I scroll down and I look for RREF. There it is, RREF. And I want to take the RREF, the reduced row echelon form of matrix B. So I go back to the matrix menu, make sure I'm in names, and I want matrix B. I press enter, and there I get X is 0, Y is 2, Z is 2. So that's the answer. This is a different form, but if we go back to the menu, and this is on the 84 as well, and you just do row echelon form of this matrix, that gives you what we're going to achieve right now. You've got ones down the diagonal and zeros underneath. The numbers above it are not zero, but this is the approach I want to take because this helps us exercise and practice how we do this. And this is definitely a test question to get to the REF form, the Gaussian form. And then we're going to solve for x, y, and z. But again, x is 0, y is 2, z is 2. So with your calculator, you will know if you're right or wrong right off the bat. How do I get there? Remember, the Gaussian approach. You start with this 1. You make that a 1, and then you worry about these becoming 0. And then you move on to column 2. So how can I get this 3 right here, to become a 1? 2 options. You could switch rows 1 and 2. We just switch rows 1 and 2. And I didn't realize that until afterwards. So what I did, you could divide row 1 by 3. But there is no division, you have to multiply. So you multiply by a third. You take row 1 and you multiply by a third. And if you do that, again, row 2 and row 3 stay the same, but row 1 will become 1, a third, negative a third, and then 0. Now what? You want a 0 here and you want a 0 here. The whole point of getting a 1 right here is that it's easy to achieve zeros. First of all, you could just subtract rows 1 and 2, and that 1 would become a 0. But there is no subtraction row operation. For row operations, you can multiply any number. It doesn't say divide, but we get around by multiplying by the reciprocal. And it says add. It doesn't say subtract, it says add. So what we're going to do is we're going to multiply one of the rows by a negative and then add, and that will be the same thing as subtracting. Okay, so how do I get this 1 to become a 0? I'm going to multiply row 1 by negative 1. And I'm going to add that to row 2. So negative 1 times row 1 plus row 2. Remember, whatever the row, the second row that's mentioned, that's where the answer goes in. So I want row 2 to change. So I'm ending in row 2. And then how do I get 2 to become a 0? I'm going to multiply row 1 by negative 2. Negative 2 times negative 2, this times negative 2, this times negative 2. So that's 4 numbers. And then take these 4 numbers and add it to these 4 numbers. And I really don't care what these are going to become, but I know that this 2 will become a 0. So negative 2 times R1 plus R3. And when you do that, you get this. And then here's that same matrix right here. Now column 1 is perfect. You have a 1 up here and zeros underneath it. Remember, you want a 1 down the diagonal from upper left to lower right. So now the next thing is to make this become a 1. Getting a 1 is always the easiest. So to get this to become a 1, and I don't want to mess with this 0. I want this to remain 0. I can multiply row 2 by the reciprocal of this. So I'm going to multiply row 2 by 3 halves. And this is how this is such a clever algorithm, because getting column 1 done, making this a 0, it doesn't matter what I multiply row 2 by, this will always be 0, right? So I'm going to multiply row 2 by 3 halves. So that will make this a 1. That will make this 7 over 2. And that'll make this 9. Row 1 and row 3 did not change. Now I want the number underneath the 1 to be a 0. I want 4/3 to be a 0. So I'm going to multiply row 2 by this opposite. I'm going to multiply row 2 by negative 4/3. And then I'm going to add that to row 3. So multiply row 2 by negative 4/3 and then add it to row 3. Again, if I multiply 0 by negative 4/3, it's still 0. And 0 plus 0 stays 0. So the zeros stay there. And when I do all that, so negative 4/3 plus 4/3 is 0. 7 halves times 4/3 is negative 14/3, plus 11/3 is negative 3/3, and negative 3/3 is just negative 1. 9 times negative 4/3 is negative 12, and negative 12 plus 10 is negative 2. Now column 1 is done, column 2 is done. I just need this to become a positive 1. So I just multiply row 3 by negative 1, and there I have it. So this is what's called row echelon form, REF. Now I use back substitution to find X and Y, because I know what Z is. Z is 2. And remember, I forgot to mention this again, but at any point, you can rewrite every row as an equation that would form a system of equations at any point. And at this point, I will refer to it. The top row becomes this, the bottom row is this, the third row is this. That third row is very telling. I know that 0x's plus 0y's plus 1z equals 2. That tells me that z is 2. And now here's using the back substitution. Now I take this equation and I replace z. Since z is 2, I get to plug that in for z. And I solve for y. So the 2's cancel out. I discover that y equals 2. Now I know what z is and I know what y is. So I take the y value, and I know what z is, I know what y is, so now I take this top one. This is the idea of working backwards, back substitution. You start with the bottom one and you work your way backwards. The top equation was that. I know what z is already 2, and I just discovered what y is 2, so I replace the y and the z with 2. And I discover that x is 0. So I know z, I know y, I know x, and I know my answer. It's an ordered triple. And I knew I made that mistake there. I didn't put it in order. X comes first, then Y, then Z, just like the alphabet. X was 0, Y is 2, Z is 2. That is the ordered triple. All the way back to this system. If X is 0 and Y is 2 and Z is 2, then the result is 0. If I plug those into here, the result is 6. If I plug those into here, the result is 10. Out of all the possible ordered triples on each of these planes, only one of them is on all three. And that one is 0, 2, 2. Last equation. Last video, rather. Last example. All right, so this is an interesting problem. You have the entire world's population reduced to 200 people. If it was just 200 people, what are the proportions of all these people? And let's see, I've got out of all the let's see, there are 138 Asians, Africans, and Europeans. That meant to be 183, I think. Yeah, I reversed those. So if you take all the Asians, Africans, Europeans, and Americans, that's a total of 183. And the number of Asians exceeds the number of Africans. Well, so just read this paragraph, and we're going to convert these to a system. I already know that my variables are given to me. W is the amount of Asians, X is the amount of Africans, and so on. So the first sentence says, if I take all the Asians plus all the Africans plus all the Europeans plus all the Americans, then the total is 183, just US apparently. The second sentence, the number of Asians exceeds the number of Africans and Europeans by 700. So remember, Asians is W. So if I take all the Asians and if I take away the Africans and the Europeans, I would still have 70 people left over because Asians exceed all the Africans and Europeans together by 70. The third sentence, the difference between the Europeans and the Americans is 15. So Europeans is Y, Z is Americans. So Y minus Z, all the Europeans minus all the Americans, you'd still have 15 people left over. And then finally, if you double the amount of Africans, that population exceeds all the Europeans and all the Americans by 23. So Africans are the X's. So doubling that would be 2X. That exceeds all the Europeans and Americans by 23. So if you double all the Africans and then subtract all the Europeans, subtract all the Americans, you still have 23 left over. So this is the system, 4 variables. So 4 axes that are all perpendicular to each other. And putting this into a matrix, I need one little step because I need all the variables aligned in column, and I have WWYX. That's not good. I need all the W's right here. All the X's are right here. All the Y's right there. So I'll put in placeholders, put in 0, 0W, 0W, 0X, etc. And now I can put it into my augmented matrix. And again, you can go to your calculator and then just do REF, and that will tell you the solutions. So right away, there are 122 W, so 122 Asians, 28 X's, X represented Africans, 24 Europeans, 9 Americans, etc. This is called the Gauss-Jordan. Well, you would use something called the Gauss-Jordan method to get here. So it's like the first one where you get the ones down the diagonal and you get the zeros underneath. The only difference is you also get the zeros above it. And then that would be, there's nothing else to solve. It's completely solved for you. but we're going to do it with just REF. So REF gives you the ones down the row and it gives you the zeros underneath. And we're not going to go through the row operations. We're just going to use our calculator. Our calculator, REF of this matrix gives us this. And now I can convert this to a system. W plus X plus Y plus Z is 183. X plus Y plus half of a Z equals this. Y plus 2/3 of a Z equals 30. And Z equals 9. So right away, now I use back substitution. Z equals 9. So I could go backwards, plug that into here, and solve for Y. So 2/3 times 9 is 6. I discover that Y is 24. So now I know Z and Y. So I go backwards yet again. I replace Z and Y with 9 and 24. And I use that to find X. So just I'll show your work, of course. X is 56 over 2. So that equals 28. So there are 28X, and X was the Africans. Now I know X. I know Y, and I've known Z for a while now. I know X, Y, and Z. So I go to the top equation to find W, and I replace X, Y, and Z with their appropriate values, and I discover that W is 122. And so that's how we get our answer. This page right here, we're almost done. This page, use my calculator to do REF. That gives me the ones down the diagonal and the zeros underneath. Then I use back substitution to solve for all my unknowns. And you can always check if you're right. If you have your calculator, you type in RREF, reduced row echelon form, and that will tell you the answers right away.